Okay. Hi everyone, thanks for coming this early. Our speaker today is Professor Syed Jafar from University of California, Irvine. And we should be really thankful to him for fitting a talk in these fields. He's being here. He's already here for 2 or 3 days and agreed to come and very curious. The title of his talk, which I found really interesting, is how many speakers can talk for 30 minutes each in one room within 1 hour and with no interference with each other's audience. So without further delay,
Thanks. So basically what the talk is about is the capacity of wireless networks, and specifically interference networks. So we will look at a little bit of cooperation later on, but most of the talk will be just these kinds of networks. You have some set of transmitters, some set of receivers, and the transmitters are trying to send their messages to their corresponding receivers without any cooperation with the other nodes. So in very simple terms, this problem could also be phrased as the following question. You have a room and there's a whole bunch of speakers. Let's say there's 100 speakers in the room. And think of it like you're trying to organize a conference, and these are speakers, and they're all going to give 30-minute talks. Okay. And each audience member is only interested in one session or one speaker. So each audience member wants to listen to one of the speakers. There may be more than one audience members that want to listen to the same speaker, but for each audience member, there's only one speaker they want to listen to. So then the question is, how many talks can you have, or how many speakers can you invite when all you have is one room and you only have that room for 1 hour? So the conventional answer, of course, would be that you should have 2 speakers, because each speaker can talk for 30 minutes. You only have 1 hour, and you're not allowed to interfere with the other speakers. But we'll see that there's something more you can do. Oh, by the way, there's no propagation path loss kind of example going on here. I'm not assuming that the room is so big that you speak in one corner and you're not heard in another corner. So everyone is within earshot of each other, and that's when this question is asked. So the big picture is we're interested in the capacity of wireless networks. That's the holy grail of information and communication theory. What have we been successful so far? We know the capacity of multiple access and broadcast networks, which is basically centralized networks where you have one transmitter, many receivers, or one receiver and many transmitters. And we also know the duality and nice relationships between the capacities of broadcast and multiple access channels. But as far as distributed networks go, where you don't have a centralized receiver or transmitter, we don't know that much. Recently, we do know the capacity of the 2-user interference network to within 1 bit, and that's a result by Atkins, Say, and Wong. And we also have large network results starting with Gupta Kumar's work, and the most recent paper, of course, is this one again by David Say, and that says how the capacity scales with the number of nodes. So if you have a large network, you keep increasing the number of nodes. The capacity scales as some exponent of the number of nodes, and that exponent beta depends on the propagation path loss. So alpha here is the propagation path loss. Again, I will not go too much into it because that's not the focus of this talk. So what's the open problem? What is it that we still know very little about? The open problem is if you have a finite network, let's say you have 10 transmitters, 10 receivers, then what do we know about the capacity of that channel? So we certainly cannot use the 2-user result there. We cannot also use large network results there either, because all it's saying is how the capacity grows with the number of nodes. So what can we say about a network? For the simplest example would be 3 transmitters, 3 receivers. What can we say about the capacity of that? So why is it a hard problem? The hard problem, well, the reason you'll hear most often is that, well, we do have good inner bounds. That is, we pretty much invented all the smart things there are, but we cannot prove that they are very smart because we just don't have good outer bounds. So people have been trying to show that pretty much what we can do is the best that can be done. So trying to find outer bounds, let's say, that's the best you can do. But until you prove that these are the best schemes, the question remains that after so many years, the things that we do for designing networks, are those schemes close to optimal? Or is it possible that we have not discovered other schemes that could result in huge, maybe like 10 times capacity improvement or even more? So is there something more significant to be discovered, or do we already know pretty much everything there is? So the capacity problem, of course, is hard for all those reasons. So what we'll do instead is try to estimate capacity through approximations. So that would be the approach in this talk. And the tool we will use is the degrees of freedom tool as an approximation to capacity. In the next slide, you will see mathematically what I mean by that. But here, just the intuition. For a single link, or even for a network, suppose I'm talking about the sum capacity, the total capacity of all the rates for all the messages in the network. Again, this is all intuition, not just math. So you would expect the sum capacity to be some expression in log of SNR, so log of 1 plus signal to noise ratio. There would be some gain factor here, and there would be some term outside the log. So the term outside the log is what you could think of it as the number of links, because each link would have a capacity of log SNR. So if you see twice log SNR, it's probably you can say that there's 2 links in that network. Also, D represents the kind of medium access and scheduling losses. Like if you have one link and you allow 2 users to use it half the time, then they each get half log SNR. So that's another way you could interpret the term D. And the term A, of course, is how your SNR is impacted. And that could be due to fading or array gain or coding gain and all those things. So to characterize capacity completely, you would actually need to find out exactly what this expression is. But what we will do is we'll try something less ambitious. We will try to look at high power scenarios when your P is high. And then you can see the capacity can be approximated as, you can ignore the 1, so D log AP over N. And then you can keep D log P and everything else as a constant. Okay, so up to a constant, capacity is just D log P. So basically the degrees of freedom, or D, or the number of parallel channels that you can create, that determines the capacity up to a constant for, well, this was a single user example. So the degrees of freedom is what we will try to estimate. And examples, of course, this should be all pretty familiar. I think I already described this. If you have one point-to-point channel, capacity will be log SNR, so it has 1 degree of freedom. If you have 2 non-interfering channels, like 2 frequencies, let's say, you're transmitting on 2 non-interfering frequencies, each frequency you could achieve capacity of log SNR, so you would have 2 degrees of freedom. If you have one point-to-point channel used by 2 users, they each get 0.5 log SNR, so the degrees of freedom are half for each of them, but the sum degrees of freedom is 1. And similarly, if you have 2 channels shared by 3 users, the total is 2, but then it's divided equally among them. Yes?
Where do you see the ISNR channels in a lattice?
Okay, I'll argue for it later on. Okay, I don't know if it's probably too early to answer that question, but the reason you don't see high SNR channels is because of interference, right? Wireless networks tend to be interference limited. And what I'll argue is that if you know all the channels, an interference channel does not have to be interference limited. You can avoid all interference.
You could argue we have 402 ISNR channels in the
That's true. Yeah, there you go. So mathematically, the degrees of freedom is also known as multiplexing gain in the context of MIMO channels. It's defined as capacity divided by the log of P and let P go to infinity. So as an approximation, you could write it as the true capacity C of P is being described as D times log of P plus a small o term of log of P. What does that mean? A small o of anything means this term decays much faster than log of P, or this term divided by log of P as P goes to infinity will go to 0. And again, the intuition is there's a number of interference-free links. You can also try to obtain more accurate capacity descriptions, and that would be, for example, an order 1 capacity description. And here the idea is the true capacity C of P should be approximated, or we want to approximate it with an order 1 approximation, which is C bar of P. And the constraint is that they should be always within a bounded constant of each other. This is a stricter constraint than this one. Because here you could have the error term growing with P, so it's unbounded, but it's just not growing as fast as log of P. Whereas here the error term has to be bounded.
Log P is not.
Yeah, so you could have something that grows less than log, like square root of log. It still is unbounded. Now, for the single user channel, of course, this was true. The capacity was, you could obtain a first order capacity or order 1 capacity characterization as D times log of 1 plus P. And we'll see you can, in fact, you can do that for multiple access channels, broadcast channels, and MIMO, of course. But the question, of course, is this relationship true always for every network, or is it just true for the cases that we know? We'll focus mostly on degrees of freedom, and this is just something else to think about. So is everyone familiar with degrees of freedom? I have a few slides at the beginning explaining what they are, but maybe I could go through them a little faster if people already know what it is, right? So for the MIMO channel, if all the transmitters can cooperate, all the receivers can cooperate. You have M transmitters, N receivers. You can create minimum of Mn parallel non-interfering channels, and therefore using the same intuition that degrees of freedom measures the number of non-interfering channels you can create. The capacity is min Mn log P plus some constant. So in the MIMO channel, you have you have joint processing of transmitted signals because there are multiple antennas at one transmitter, and of course joint processing at the receivers as well. But if you make one end of the link distributed, what happens? So in the broadcast channel, if you make the receivers distributed, then you still have the min Mn degrees of freedom. It's easy to see, because suppose I want to send a message to receiver 1, and I don't want to cause any interference to any of the other receivers, then I will just send that message along a vector that is orthogonal to all these other channel vectors. So the projection of my message on these other vectors will be 0, and only receiver 1 will hear what I'm saying.
For multi-axis, you get that only up to a certain multiplexing gain. So you're only talking about degrees of freedom, you're not talking about the gain at which it's only. How is this related to diversity multiplexing?
I'm not focusing on the diversity dimension at all. I'm only focusing on the multiplexing gain side of it. Okay, because I'm only interested in capacity, no BER consideration here. So really, the distributed processing of the receivers doesn't hurt the multiplexing gain. You can still create min of Mn parallel channels. The same thing for multiple access channel also. If you have M distributed transmitters, but you're able to jointly process the received signals, then again, if I want to hear, let's say I want to hear only transmitter 1, and I don't want to hear on any other, or I want to decode transmitter 1 alone, while zero forcing everyone else, then what do? I just take this receive vector and project it along a vector that's orthogonal to all the other users' channel vectors, and that'll zero force everyone else. And you can do that many times, minimum of Mn times. You can create that many parallel channels. So we saw that on the MIMO channel, you have min Mn degrees of freedom, and that's the same number of degrees of freedom when either transmitters or receivers are distributed. But what happens if both the transmitters and receivers are distributed? So that's now the interference channel, because neither the transmitters can cooperate nor the receivers can cooperate. So the two-user interference channel, if this was a MIMO system, of course, if the transmitters were able to cooperate or the receivers were able to cooperate, you would have 2 degrees of freedom, because you have min of Mn, and M and N are both equal to 2 here. Of course, the capacity of this is known to within 1 bit, like I said before, and you can show that this interference channel has only 1 degree of freedom. So the sum capacity of this interference channel, where transmitter 1 is only trying to talk to receiver 1 and transmitter 2 is only trying to talk to receiver 2, and they interfere, that capacity is only a single user capacity up to an order constant. So the capacity is still, the sum capacity is log of 1 plus p, which would be the capacity of only one user. So basically that tells you the sum capacity is equal to single user capacity, which means that the best you can do is orthogonalize the users. So if there's 2 users, they want to both talk, you let one of them talk half the time, the other one talks half the time. So they both get half log SNR. So in the end, you get full.
An assumption that it's interfering gains are strong than...
No. It's for anything, for any gain. Strong and weak, if interference was strong, you would actually know the full capacity, the exact capacity. But here we're talking about degrees of freedom. And that's the reason I'll tell you the degrees of freedom is a very useful tool, because in most cases, for the general interference network even, or for pretty much any wireless network, we'll be able to find the degrees of freedom. But of course, we don't know the capacity. Okay, so we'll be able to approximate capacity up to a constant, but not find the exact, up to a bounded constant, but not find the exact capacity.
So you're saying that TDM is optimal in which case?
At high SNR, suppose everyone's power is very high, and I'm interested in the total capacity, okay? Then the best thing to do is to avoid each other. Okay.
Just to extend that question, is it because like the cross gains are still unity and direct gains it's not as if the cross gains are high or low as compared to a direct gains. Is it because of that reason?
Say that again?
Like is
No, no,
it-
no, no, so no. There's no assumption on the gains here. You could pick any gains as long as they're not all equal. I mean, if you have, well, in this case, even if they're all equal, you still have only 1 degree of freedom, so it doesn't matter. You can choose any gain values that you want. So the intuition here would be the degrees of freedom, again, correspond to the number of interference-free channels. But if you have only one antenna at every node, then you cannot eliminate interference. So that's how you may argue that that's probably why there's only 1 degree of freedom. Of course, we'll question this intuition, and we'll see that it's not exactly correct. Now, what if you have multiple antennas at every node? So there's still 2 by 2 interference channel, 2 transmitters, 2 receivers. Again, transmitter 1 is only trying to talk to receiver 1. But you have multiple antennas, and possibly different number of antennas at every node, so M1, N1, M2, and N2. In that case, you can still find the degrees of freedom, even though the capacity is not known. And you can show that the capacity here is this term times log of P, where P is the total power for all the two transmitters, plus a constant term. I mean, it's within a constant term of that. So if you look at this term, what it's saying is the capacity has to be less than equal to, because there's a min outside, the max of M1, N2, M2, N1. So basically, the capacity cannot be more than the maximum number of antennas at any of these nodes, which is, again, consistent with the old intuition that, well, if I have that many antennas, that's probably the maximum number of non-interfering channels I could create. And in all these cases, it's just zero forcing that you need to create these parallel non-interfering channels and achieve the degrees of freedom. So now let's go to the full K-user interference channel. So now you have, now I explain this a little bit more in detail because this is the model we'll study. You have K transmitters, same number of receivers as well. Each transmitter has a message only for its corresponding receiver. So transmitter 1 does not have a message for receiver 2 and so on. It's only a message for receiver 1. Now, if the channel coefficients are constant, that is, they're not changing with time, they're not changing with frequency, but just fixed. That's the standard information theory model. Then the conjectures, there's a conjecture before that the capacity of this channel, where P is the total power of all the transmitters, is the same as the capacity of a single user AWGN channel within a constant, up to a constant term. So basically, this is saying the degrees of freedom of this network are only 1. It has only 1 degree of freedom. But the same paper will also find an outer bound, and the outer bound is K by 2, that you can actually have not more than K by 2 non-interfering channels.
That's the assumption. Perfect call. The transmitters are sort of co-located transmitters, co-located receivers.
No, nothing is co-located. It's completely distributed. All transmitters, it's just that they're within earshot of each other, so they're not remotely located. I mean, all these channel gains are non-zero. Okay, but there's no cooperation going on. I mean, there's no shared messages here, and there's no other side information available.
They have individual power constraints on each node, and just that their sum is P, right?
It doesn't really make a difference. You can assume they each have power P. You can assume they have a total power P, because we're looking at high. I mean, when you talk about degrees of freedom, you're scaling by log of P, right? So whether it's log of P or log of Kp, which is log of P plus log of K. But log of K is small compared to log of P. It doesn't really make a difference, because P is going to infinity anyway. So then what's the intuition here? So you see that the conjecture is way off compared to the outer bound, but still that's what we believe in. In general, we tend to place greater faith in our inner bounds than our outer bounds, because, like I said, the notion is that the belief is that the outer bounds are just not that good.
So I think your question really was, when they got their outer bound, what assumption, they typically put
Oh.
an outer bound like having some
Okay, so
extra bonus, right? And
yeah.
bonus.
So first thing is not just complete cooperation, because if I allow full cooperation, I'll get K degrees of freedom, because then I'll have a MIMO system with K antennas on either side, so I'll have K degrees of freedom. So how come it's only K by 2? Well, the way to argue that is, let's consider only 2 messages at a time. Let's set all the other messages to 0. Now that cannot hurt these 2 messages, right? Setting all the other messages to 0 cannot hurt, let's say, messages W1 and W2. Now we know that for the 2-user interference channel, there's only 1 degree of freedom, which means that the degrees of freedom for message 1 and message 2 must add up to 1. I mean, it cannot be more than 1. And then by considering 2 of them at a time, you can just consider all possible choices of 2 messages here. Each of them has to add up to 1, and then add them all up together, and you will get the total degrees of freedom cannot be more than k by 2.
Oh, that seems like a really loose bound. I mean, because if you're not doing them all at the same time, which means you're sort of picking a band or something. I don't.
Yeah, of course. I mean, again, the impression was, of course, it's loose. Otherwise, there wouldn't be a conjecture that this is the best we can do. So just interpretation. How do we interpret this? Well, the conjecture is what the conjecture is really saying is that if there are 100 speakers, there's 100 users. Then it's optimal for each of them to speak 1% of the time. So the total capacity would be the single user capacity, right? 1% times 100, you would get just 1 back. But the outer bound is saying something different. It seems impossible right now, but we'll see it's possible later on. That what the outer bound is saying is that there are 100 speakers, they cannot speak for more than 50% of the time. That's what the outer bound is saying, okay? With no interference. So let's answer the question in the talk. How many speakers can talk for 30 minutes in one room within 1 hour, no interference to each other's audience? And the answer is unlimited, because that's what the outer bound is saying also, that no matter what k is, you can get k by 2 degrees of freedom. That's everyone can talk half the time. So everyone can get capacity 1/2 log SNR. So how does that work? Well, suppose I pick so in this example, I will actually construct the channel. Later on, I'll relax that assumption. But right now, I'm actually picking the locations of the speakers. So I'm a conference organizer in this room. I'm trying to place the audience members and the speakers. And the way I do it is I want the delay for each desired link, that is the link or the distance between between a speaker and his desired audience member. That distance should be such that it takes sound an even number of time slots to travel that distance. So let's say the basic unit of time is t0 symbol. A symbol duration is t0. Then it takes an even number of t0s for sound to propagate from the speaker to a desired audience member. And it takes an odd number of time slots to go to an undesired member. So you're trying to place the speakers and audience in a way such that all desired links have a propagation delay even multiple of t0, and all undesired links have a propagation delay of an odd multiple of t0.
The propagation delay is more than symbol time?
Well, depending on how you define symbol. The symbol time can be pretty small, right? So it's just, again, this is a toy example, okay? Yeah, some t0, not just. So for example, here, the squares are the speakers and the circles are the audience members. These circular nodes, the blue nodes want to listen to the blue speaker, the yellow ones want to hear the yellow speaker, and the red ones want to hear the red speaker. The square is the speaker, red is the audience. But the constraint is that you should not hear any interference. So this blue guy, when he's listening to the blue square, he should not hear this yellow guy, and he should not hear the red guy. Similarly, when the red guy is listening to the red speaker, he should not hear the blue and the yellows. So how does that happen? Well, here's how it happens. All transmissions occur simultaneously over even slots. So everyone speaks over even slots together, okay? And everyone listens also only over even slots. I mean, all the receivers listen. The speakers don't listen, and the receivers don't transmit. So what does that mean? So if you think of the blue guy, the delay from his desired speaker is an even multiple of t0, but the delay from the non-desired speakers is an odd multiple of t0. So he will hear his desired speaker at an even time slot, because everyone's speaking at an even time slot, and the delay is even. So even plus even is even for the desired transmission. However, the delay for an undesired transmission is odd, and the undesired transmission also takes place at an even slot, but even plus odd is odd, so you will hear him at an odd slot. So basically, you hear everyone you don't want to hear in an odd slot, and you hear the only person you want to hear in an even slot without any interference. So just to show how that would happen here. So let's say this circle represents all points that are distance t0. So it takes one symbol duration for sound to travel from the speaker up to this circle. And so all black circles represent odd number of delays, and all red circles represent even number of delays. So you can see that the blue nodes have been placed, or the blue audience members have been placed such that their delay to the desired speaker is even, because they're on a red circle for that speaker, but they're on a black circle for non-desired speakers. So the delay to the non-desired speaker is odd. And similarly, the delay to this speaker is also odd. So you will hear them only over odd time slots.
So if you abstract it, this is somewhere 0 force and other guys.
It's interference alignment. What you're trying to do is make sure you know everyone's speaking half the time. So half the time you are going to hear somebody that you don't want to hear. But what you're trying to ensure is it's the same half of the time that when you hear everyone that you don't want to hear. So all the interference terms should perfectly overlap, leaving the half of the time that you really want to hear your desired speaker free from interference. Okay?
I think it is a
Yeah, it has to be, right?
because I mean you're getting a receiver which sees no interference by some transmitter matching.
Yes, well, yeah. That's how we'll later interpret it anyway. So the point here is that you can have, and this is an example for 3, but you could do it for more users also. So you can have,
Really good for, like, you mean do these examples of the circle?
yeah, actually it gets uglier as you increase the number of users. These patterns don't look so pretty. Like with 4, we tried with 4, and with 4 also you can do that arrangement. But what you can do is if you have a large number of users, you allow yourself an epsilon overlap. So you back off from half by an epsilon. That means you don't have to exactly sit at the intersection of the circles, but you have to be within epsilon of the intersection. In that case, yeah, you can find like as many audience members and as many speakers as you want. But of course, like I said, in this case, I'm actually designing the channel. But in typical interference networks, the nodes are just randomly placed, and the channel is decided by nature. And then what can I do?
Instead of introducing even odd time slots, what if you assume everyone gets at the same time because the distances are not so much different in the room, but you introduce delays?
That's introduced delays don't really help because it's introduced for everyone. When you introduce a delay, it affects all the receivers the same way. Whereas what you're counting on here is that between each transmitter and receiver, you're free to pick a different delay, and that's what distinguishes the signals. Okay, so introduced, I mean, unless the physical channel already has a different delay for each link, which is truly the case. Always, I mean, distances are different, right, between any pair of nodes. So introducing delays artificially doesn't really help because it affects all received signals the same way. Okay, so this is the usual information theoretic interference channel. There are no delays here. So all transmitted signals are received together at the same time at every node. And the channel coefficients are also random. We're not picking the channel coefficients. I'm not designing the channel. So what you can show here is that if you consider a 2n+1 symbol extension of the channel, what does that mean? That means you use the channel 2n+1 times. So let's say n is equal to 1. Then I'm using the channel 3 times, which is saying that I'm coding over 3 symbols at once. So think of 3 channel uses as being 1 super symbol. So in this 3-dimensional vector space, that's what I'm coding. Okay, and then what you're able to do is achieve 3n+1 degrees of freedom. So if you use 3 symbols, you will be able to achieve 4 degrees of freedom. Okay, so you could say that d, or the degrees of freedom, has to be greater than or equal to 3n+1 over 2n+1, and you can do this for any n. Okay. It's not obvious actually. Especially when you increase the number of users, it's not even this. Actually, it gets a lot messier. In fact, it's quite. If you think about it, it would be quite obvious that you cannot do it, and then it would be surprising that in fact you can. And in the next slide, I'll argue why it's actually counterintuitive that you can do this. But suppose you believe this, then because you can do this for any n, and for large n, this term will go arbitrarily close to 3/2, which means you can achieve 3/2 degrees of freedom per orthogonal time and frequency dimension. So it's not that I'm gaining something by just using more time. It is normalized by the number of time slots I use. So basically what we're showing is that for any epsilon, we can come up to 3/2 minus epsilon log SNR as the lower bound. Of course, the outer bound already we know is k/2, so it's 3/2 log of SNR plus order 1. Now, on the other hand, you would also notice that we're not exactly achieving 3/2. We're just getting arbitrarily close to 3/2. But turns out if you have more than one antenna at every node, so every node, let's say, has 2 antennas, that's enough. all nodes have 2 antennas, then you can achieve exactly 3m by 2, which means you just consider a 2 symbol extension and you'll be able to achieve 3m degrees of freedom. So you would not, there's no n here anymore. So you, in this case, you have actually the order 1 capacity, because you can say the capacity is 3m by 2 log of 1 plus p plus order 1. Whereas in this case, you have the degrees of freedom, but you don't have an order 1 capacity characterization. So this is the first example where there's a distinction between the two. In every case so far, multiple access, broadcast, even the 2-user interference channel, the degrees of freedom give you the order 1 capacity characterization, because it's all, capacity is always just d log of SNR plus order 1. So how does this work? This works through interference alignment. And like I said, this is the example where n is equal to 1, so you're working over a 3-dimensional space. In this 3-dimensional space, what will happen is user 1 will transmit 2 vectors or 2 messages along 2 directions. So he will achieve 2 by 3 degrees of freedom, because he's sending 2 messages, but he's using this 3 symbol extension of the channel. Whereas user 2 and user 3 will send only 1 message. So they will achieve 1/3 degrees of freedom. The total will be 4/3. That's what we can do with n is equal to 1. Yes? Yes, it could be. In the next slide, we'll actually make that a little bit clearer. This is just a picture to show you what's aligning with what. So basically what's happening here is user 1's, so this is user 1's receiver. He's interested in the 2 messages user 1 is sending. And those messages have been sent along these vectors v11, v21. So v11 and v21 are the directions that he's interested in. Of course, these directions get modulated by the channel through which they arrive. But the things he's not interested in, that is the messages from user 2 and user 3, or transmitter 2 and transmitter 3, it's important to know that they're the ones getting aligned. So here, if you think about it, we're considering 3 dimensions. It's only a 3 symbol extension. But there's 4 messages being sent, 1, 2, 3, and 4. So you're looking at 4 messages in 3 dimensions. Something has to overlap with something else. But the key here is that you want things that you don't care about to overlap, so that the things you really want, you can separate them out. And because you have the slides, you can look at it later. You can basically solve these equations that for these two to align, and you can pick the direction you want them to align to. For example, here I want everything to align along the vector 1, 1, 1, things I don't want. So then that means h12 v2 should be equal to 1, 1, 1, which means you can find what v2 is. v2 is just h12 inverse of that, and similarly v3 and so on. So you can find the directions also. So what does that give us? That doesn't give us the capacity region. So far in my talk, I always talk about some capacity and the total degrees of freedom, but really you can find this for the whole degrees of freedom region, not just the sum capacity. So the degrees of freedom region for the 3-user interference channel is this. It's these inequalities, D1, basically the same inequalities you would have if you considered the 2-user interference channel one at a time. So there's 3 2-user interference channels in this, and each of them have degrees of freedom bounded by 1. So D1 plus D2 less than equal to 1, D1 plus D3 less than equal to 1, and so on. That's the degree of freedom region for this 3-user interference channel. You can plot it, and that's what it looks like. What does that mean? That's basically the capacity region up to an approximation of small o of log SNR. And of course, this is the best point to be at. Here's where every user is achieving half his high SNR capacity.
Oh, so there's no, so you got only these 2 user constraints, and yet you get actually 3 by 2.
Yes. So because what we're saying is, when you add users, first user of course gets the full channel. He can transmit log SNR. Second user comes in, they have to the first guy has to back off, and they both get half. So they're sharing just like you would. But after that, nobody hurts anybody. You can keep on adding users. Everyone will still get 1/2 of the channel capacity. So as you add more users, there's no competition going on after that. So once you're back at half, you're good.
Yeah, but they have to do something very smart to do that.
Yeah, they have to align the interference, right? So what's the result with general k number of users? So any number of users. So if you have k users, and let's say you have single antenna at every node, then the same 3-user kind of, you can extend it. I didn't even show you the derivation for the 3 case. In this case also, you don't see the derivation. But the result is that you can come within epsilon of k by 2 log of 1 plus p.
So with k users, like you are getting somehow all of the things you don't care about, the interfering signals, are all in how many dimensions do those signals occupy?
Right.
They're maybe K by 2.
What's that?
It's truly K.
Intuitively, if you think of it, that's the best you could have done anyway, because when you have somebody else, if you have somebody else transmitting, they will kill one dimension, because that interference signal will come to you at least along one dimension. It cannot be less than one dimension. So if you just consider 2 dimensions, at least one of them will be wasted by the other guy. Now all you're saying is no matter how many other guys are there, I will just make sure they all kill the same dimension. They don't actually come over and leak and kill the other dimension stuff.
They're actually going to kill half of the dimensions. You're going to somehow always have all the interference in half of the dimensions.
Right. And it's counterintuitive. Let me say why. Of course, maybe you already see it's counterintuitive, because suppose there's k users, and suppose each of them is picking a direction to transmit along. Then there's this basically k things you're picking. Okay, think of a direction as a variable. Then there's k things you're picking. But now look at one receiver. Let's say receiver 1. At receiver 1, you want the interference from transmitter 2 all the way through k to align along one dimension, right? So basically, you have how many constraints? You want transmitter 2 and 3 to be parallel. You want 3 and 4 to be parallel, and so on, basically. So you have k minus 1 constraints. But there's k receivers. Each has k minus 1 constraints. So basically, the number of constraints is of the order of k squared, whereas the number of variables of the order of k, because you're only picking k directions. So it seems like in impossible situation, you have fewer variables and more equations that you're trying to satisfy.
But you're assuming they're cooperating, when you say they're case by case.
There is no cooperation.
Still, you're solving them jointly, right? When you say
Yeah, we're solving them. So what do I mean by cooperation? By cooperation, I mean they don't know each other's message, but they know all the channel knowledge. I mean, they have all the channel knowledge, so they can pick their directions optimally.
A priori code construction.
But you're saying if each one of them tries to avoid each other's signal, there's one solution. I mean, they would in effect be still solving that case per equation k variable problem.
Yeah, except these are not linear equations, so it doesn't.
Yeah, it's not equation, but
Right.
they end up operating in a regime where everyone else's interference is only in one dimension.
Right.
So this is the planar case, right? A linear case, do you think you get more degrees of freedom? I mean, you are solving that in a plane like this.
I don't think this is any geometry.
Yeah, the geometry doesn't matter here. It's just every 2 nodes have a link between them, have a channel coefficient between them. Their location doesn't really matter.
So for k users, you create this higher dimensional signal space, and how many dimensions is there?
Oh, so the number of dimensions I will need will keep on growing. So just like in the 3 user case, I needed 2n plus 1 dimensions to get 3n plus 1 degrees of freedom. So the degrees of freedom per dimension, that is per orthogonal time or frequency dimension, is going to 3 by 2. But I am constructing my codes over these bigger and bigger super symbols. Depending on how close I want to get to 3 by 2, I'll need to have that much bigger symbol extension. But one thing I should mention is the channels are fading or they're changing. I need that, otherwise you cannot have things aligned differently. Because if all the channels don't change, then all channels are basically, even if you consider a multiple symbol extension, it's just a multiple of the identity matrix. So there's no rotation going on.
So they also know everybody's channel. So
Yes.
one person is for the entire channel.
Yes. So a transmitter even knows the other transmitter's channel to the receiver. That's the assumption here.
So what do you think is now about the channel changing?
Oh, so you need the channel, because the key here is that to do interference alignment, what you want is the channel between any node pair, any transmitter to any receiver, to be distinct from the channel from other node pairs. So each of them should be different, because each channel basically represents how the signal is getting rotated, right?
It's not, it's a different channel. That's what you're saying, right? If you have
Uh,
two
I
plus
mean, if you
one,
have one fixed instance of randomly chosen channels, right?
That's not enough. So I will need, when I say I consider a time extension, like I consider 3 symbols, I want the channel to be different over those 3 symbols. That is, the channel coefficient value should change from symbol 1 to symbol 2 to symbol 3. So time varying channel or a frequency selective channel, if I'm considering 3 frequencies, then I want the channel on each frequency to be different. Otherwise, you cannot align anything. Everything is rotated by the same amount. So really, it's the channel fading that's helping you here. It's not the same thing as diversity, though, because you don't really want them, or you don't care about them being statistically independent. All you want is for them to be different. That is, they should be jointly have a continuous distribution. Okay.
In the figure you showed you a lot of matrices, you want them to be as close to full rank as possible.
No, they're all diagonal matrices, because see, when you consider orthogonal channel extensions, it's just diagonal matrix, because every time slot there's only one channel coefficient. One time slot doesn't interfere with the other one, so there is no cross terms. All I'm saying is these diagonal terms should not be, the channel extension should not be an identity matrix or a multiple of the identity matrix. It should be distinct terms. So what if every user had M antennas at each node? Or yeah, so every user had M antennas. Well, the simple way to argue about that case would be, let's think of those M antennas as being M users. So let's distribute the system completely. Even though you had K users with M antennas, you could think of it as M times K users with one antenna each. In that case, you would get M times K over 2.
So you're using M in both the transmitter and the receiver?
Yes, everyone has M antennas. How about if they have different number of antennas? Let's say ith transmitter has TI antennas, ith receiver has RI antennas. Again, you can split the ith transmitter receiver pair into a minimum of TI, RI, non-interfering, distributed users, and throw away the extra antennas. And then you would get, there should be a half missing. So there's a half outside. If you had full cooperation, you would get this. So what this is saying is that interference costs no more than half the degrees of freedom, or interference costs no more than half your capacity at high SNR. It doesn't matter how many interferers there are. This is not tight though. You can actually have more than this. For example, if you had 2 transmitters, each with 2 antennas, and 2 receivers, each with 1 antenna, you could get 2 degrees of freedom, but this is only saying 1. So this is not tight, but all this is saying is that you do not lose more than half. You may not lose anything, but if you have enough antennas. So what does that mean? So the prior belief, of course, is that co-located, if the systems are, if you have interfering systems and they're right next to each other, so they hear each other pretty loud, then they must be orthogonalized. Otherwise, the system becomes interference limited, and there's no use to increasing your power, because the interfering guy will also increase his power, and then it just doesn't help anyone. However, the new insight from this result is that any number of interfering systems, so K could be any number, can coexist per 2 orthogonal channels without being interference limited. So they'll all have a capacity that scales like log of 1 plus p, half of that. Because the proof is in the papers. With 1 hour, I really don't have time to go through the proof, but. So the same thing, at high SNR, regardless of the number of interferers, you can achieve half the capacity with no interference. And specifically, if you compare it to the prior conjecture that the capacity is always just log of SNR regardless of the number of users, there's a huge capacity gain. So if you have 3 users, the capacity is 50% higher. If you have 20 users, it's 900% higher. If you have 100 users, then it's 4,900% higher. But of course, everyone has to know all the channels. So now let's consider, again, wireless networks. Interference channel is one kind of wireless network, but there could be other situations. For example, the most general case would be where everyone is allowed to talk to everyone, and that's called the X channel. So this is the X channel, 2 transmitters, 2 receivers. Transmitter 1 can talk to receiver 1, that would be the message W11. It can talk to receiver 2, that would be the message W21, and so on. So there's 4 messages. So this is a general case because it includes the multiple access channel, it includes the broadcast channel, it includes the interference channel. If I just set these messages to 0 and only consider messages W11 and W22, it's the interference channel. And of course, it has a Z channel and all those things in it. So if you find the capacity region of this, then you solve every single scenario that's a special case of this. So we'll find, of course, not the capacity region, but the degrees of freedom of this. So first I'll explain, again, using a time delay example. Actually, the converse I'm not going to prove again in the slide, but the converse you can show if you have 2 transmitters, 2 receivers. Remember, the interference channel had only 1 degree of freedom for 2 transmitters, 2 receivers. But this guy, the X channel, can have 4 by 3 degrees of freedom, which is 33% higher. That's the converse. The converse would only say the capacity has to be less than or equal to 4 by 3 log of p. Now, the time delay example will show you how you can do that. So suppose there's a blue receiver and there's a red receiver. And both transmitters have, of course, a blue message and a red message. So the blue message is meant for the blue guy and the red message is meant for the red guy. So by my definition, this is red. But of course, these are different reds, so they're not the same message. Okay, so there's an independent blue message here and a different message here. Now these are the delays. Suppose I can arrange these guys so that the delay from transmitter 1 to both receivers is just 1 unit of T0, and the delay from transmitter 2 to, I mean, the geometry kind of suggests that is 3, and that's 2. Okay, and then they transmit in the following way. The transmitter 1, these are time slots, sends the message for receiver 2, then receiver 1, then nothing, 2, 1, nothing, and so on. And similarly, transmitter 2 sends receiver 1, receiver 2, nothing, 1, 2, nothing, and so on. And if you just do the math, find out how things line up, you will find at receiver 1, he's interested in the blue messages. The blue messages do not interfere, but what will happen is the red from here will overlap with the red from here, so they'll interfere, but you don't care about the red messages, so it doesn't matter. Similarly, at receiver 2, you care about the red messages, but the blue messages will line up, so they'll be heard on top of each other. They'll cause interference, but you don't care about those, so don't worry about that. So, because it's an X channel, and the blue message is from transmitter 1 to receiver 1, the red message is from transmitter 1 to receiver 2. So basically, what is each receiver getting? He's getting 2 messages in every 3 time slots. So basically, he's getting 2 by 3 degrees of freedom, and total is 4 by 3 degrees of freedom. So you can get it this way. But of course, now going to the standard information theoretic model, there's no delays anymore. All the channels arrive at the same time. And what we're trying to show here is that, again, the same thing. You can use interference alignment by considering super symbols of multiple channel uses. So in this case, also you're considering symbols, a three symbol extension. So you have three time slots, and the channel takes a different value over each time slot. Then your goal is to make sure the signals cast overlapping shadows at the receivers where they constitute interference, and they cast distinct shadows at the receiver where they're desired. So in this case, transmitter 1, basically the yellow messages are meant for receiver 2, and the blue messages are meant for receiver 1. So what happens is you pick, and it's important to note that each of these channels is a different rotation. That's what you need for interference alignment. That H11 is a different rotation from H12 and so on. So that's why they can align differently at different places. So after things pass through H11, the yellow and orange, which are not meant for receiver 1, they align and they eat up only 1 dimension. So there's still 2 dimensions left for you that are free from interference. And it is from those 2 dimensions that you will get your desired messages. And similarly, receiver 2 does the same thing. So the capacity in this case is 4 by 3 log of 1 plus p plus order 1. Of course, the channel coefficients are all random here. I'm not picking the channel coefficients. And also in this case, it turns out you need less information. The transmitter 1 does not need to know these channels. Okay, so each transmitter needs to know its own channel, not the other guy's channel. So if you find the degree of freedom region in this case, it's a 2-user X channel. It has 4 messages, so I would really need a 4-dimensional region to plot it. But this is plotted for, let's say, D22 is fixed at a value that, in this case, is 1/3. I didn't really label the axes anyway, so it doesn't matter. But that's what the degrees of freedom region looks like. And mathematically, this is the entire degree of freedom region. But this is what it would look like if you fixed D22 at 1/3. If you take D22 to 0, then it would be the same as the interference channel degree of freedom region. So here's, well, this is as good as a proof as you will see for the achievability for the X channel. So you're considering 3 symbol extensions. They're all diagonal, of course. So symbol 1 represents time instant 1. So of course, it's not going to interfere with time instant 2. So you only see this X channel, which is completely independent of the X channel at time instant 2, and an X channel at time instant 3. Right? So all channels, channel here to here is the diagonal channel. So what happens here is each receiver says, you can pick any vector, but for this example, each receiver says, I am willing to accept interference only along direction 1, 1, 1. So I'm in this 3-dimensional space. I'll assign 1 vector, and you're allowed to send me interference only along that direction. So this guy is accepting interference along 1, 1, 1, and so is this guy. So what does that mean? When transmitter 1 sends his message for receiver 2, that is going to cause interference to receiver 1. So he has to make sure that that interference reaches receiver 1 along the direction 1, 1, 1. So this is the message for receiver 2, sent from transmitter 1. So you have to pick the coefficients or the beamforming vector in this case. So you see A1 over A1 will give you 1, A2 over A2 will give you 1, A3 over A3 will give you 1. So basically, when this message passes through this channel, you will see 1, 1, 1 at receiver 1. Same thing, x11 is the message for receiver 1, so it should pass through, it'll be interference at receiver 2, so here it should come out as 111. So again, you pick your beamforming direction to achieve that. So in the end, what ends up happening is at receiver 1, the two desired signals are linearly independent vectors, and all the interference is aligned. These are two interference signals. They both show up along the same direction, 111. So they kill one dimension and you have 2 dimensions left. You can get 2 degrees of freedom. So I'll do one converse proof, because we haven't done any converse proofs yet, for the general X network. So here what you have is M transmitters, any number M, and N receivers, and you can have any message. Any transmitter can talk to any receiver, and they're all independent messages. And again, the question is, what's the maximum number of degrees of freedom? And you can think of it as non-interfering communication links, although the definition is not that. Its definition is just the capacity divided by log of P, but that's just for your interpretation. So how many degrees of freedom can you achieve in this network? And I mean by the sum degrees of freedom per orthogonal time and frequency dimension. So we'll just prove a converse, and then in this case, I'll just tell you what the achievability is. So how does the converse work? Well, let's consider only transmitter 1 and receiver 1 are active. That's the short form. But what does that mean when I say they're active? That means only messages that are associated with transmitter 1 or receiver 1 are the messages I'm considering. All the other messages are 0. I don't care about those messages. Of course, setting some messages to 0 does not hurt the other messages, so that's important. I'm not helping these messages. I'm not hurting these. I'm looking for an outer bound, right? So I cannot do anything to limit the system. I can do things to help the system, but I cannot limit the system. So only these messages are active. So Wij, where either I or j equal to 1 are the only messages I'm considering. Now start with this is a converse. So let somebody else design a coding scheme. I'm only going to say this, you cannot do better than this. So somebody else designs a coding scheme, and it's a reliable scheme. They give me a reliable scheme, which means all these messages are being decoded reliably. So now what I'll say is, well, I'm going to have a genie go and tell what all the messages are to every receiver except receiver 1. I mean, other than your desired message. I'll tell you all the undesired messages. So at receiver 2, for example, he's interested in W21. So a genie will tell him every other message except for W21. So that again cannot hurt. So it doesn't violate the outer bound that I'm shooting for. So what does that mean? So now you know what's being transmitted by transmitters 2 through M. Well, yeah, receiver 2 now knows all the messages being sent from transmitters 2 through M, because these are not desired messages. So he knows what these guys are sending. He can subtract out their signals. So he will have only a signal coming from transmitter 1. And same thing, every receiver can do the same thing. So every receiver eliminates interference from all the other transmitters. Now we'll claim that receiver 1 can also eliminate the interference from all the other transmitters. Why is that? Because it was a reliable coding scheme. So receiver 1, note that all these messages are meant for receiver 1. So receiver 1 must be able to decode them. If he can decode them, then he can subtract them out. So basically all receivers in the system can eliminate the interference from all the transmitters except for transmitter 1. So this is what you end up with after eliminating things. I've only helped the system so far. Now what do you say? Well, you say everyone is just looking at the signal coming from transmitter 1. It's like a broadcast channel. Now what I can do is at receiver 1, if I reduce the noise, I can reduce the noise to make it a degraded broadcast channel, or make receiver 1 basically the strongest receiver. So then he will be able to decode everything that anyone can decode. So he will be able to decode all the messages. Notice that all the messages going to the other receivers are coming only from transmitter 1. So receiver 1 must be able to decode all messages, every single message in the network. So basically, now that we've claimed that starting with the original M by N network with transmitter 1 and receiver 1 active, receiver 1 must be able to decode all messages if you reduce its noise. But reducing its noise is not going to change the degrees of freedom. So the degrees of freedom are bounded by this multiple access channel. Suppose all of these guys were just talking to receiver 1. Receiver 1 is able to decode everything. So the capacity cannot be the multiple access channel capacity. But this multiple access channel has only one receiver antenna. So it cannot have more than 1 degree of freedom. Which means all the messages, the summation of Wij where either I or j equals 1, the degree of freedom for those messages cannot be more than 1. Okay. now you can consider all different possibilities. Here, transmitter 1 and receiver 1 were active. Now you can choose any transmitter and any receiver, make those the active one. That is, only consider messages associated with those transmitter and receiver pairs and null out all the other messages. And each time you would get a bound on the sum of those degrees of freedom, right? So how many inequalities will you have? Well, there's m transmitters. You could pick one of m transmitters. You could pick one of n receivers. So there's m times n different scenarios you could consider, each of which would give you an inequality on the degrees of freedom, an upper bound on the degrees of freedom. And how many terms does each inequality have? It has, well, the number of messages in this case was m plus n minus 1. So that's how many terms each inequality has. So you add them all up, you will see that all messages appear m plus n minus 1 times. And so it's a simple addition of the inequalities. You will get the total degrees of freedom of this m by n network cannot be more than mn over m plus n minus 1. Now in this case, if you plug in m equals n equals 2, which is the example we considered before, then you would get 4 by 3, which is what we showed before, was the converse. So what can we say from here? Well, we can say, suppose m and n were equal, so you have equal number of transmitters and receivers, then basically d is less than or equal to k squared over 2k minus 1. That's the maximum number of degrees of freedom, which is not that different from k by 2 if k is large. It's almost equal to k by 2. So really this network where everyone can talk to everyone doesn't have that many more degrees of freedom compared to that interference network where everyone only talks to one receiver, if k is large. Of course, for k small, it has a significant advantage over the interference channel. Like for the 2-user interference channel, the interference channel has only 1 degree of freedom, but the X channel has 4 by 3 degrees of freedom. On the other hand, you can also notice that if the number of transmitters is much larger than the number of receivers or vice versa, then you could achieve the min of mn, very close to min of mn degrees of freedom, which is the maximum that you could get even if all transmitters were cooperating and all receivers were cooperating. So, and well, this is all an upper bound. We are able to show it's tight when either m or n equals 2. So you could have m equal to 100, n equals 2. Then you would achieve 200 over 201 degrees of freedom. Oh, sorry, 200 over 101 degrees of freedom, which is close to 2. The best you can do. So the X channel is able to get almost the full degrees of freedom out of the network even without any cooperation. There was another section on cognitive sharing. I'll skip that because I'm running out of time here. Maybe I'll just quickly describe what's going on here. So now we're asking the question, what will happen if there's some cooperation going on? But what is the nature of cooperation? The nature is that one of the transmitters or one of the receivers, a genie has already given him the message for another transmitter. So in this case, what is this case? This is the standard cognitive radio channel in information theory. So transmitter 2, non-causally, already knows the message that's being sent by transmitter 1. And this is the interference channel. So each transmitter is only talking to one receiver. So you can show that knowing only one message, whether transmitter 2 knows transmitter 1's message or receiver 2 knows transmitter 1's message, or both transmitter 2 and receiver 2 know transmitter 1's message, neither of these cases can you increase the degrees of freedom from 1. So it's only 1 degree of freedom. Note on the other hand that if they both knew each other's message, then this will be a broadcast channel and you could really zero force and get 2 degrees of freedom. So it's not that you would always have. And also you can see that sharing a message with the transmitter is the same as sharing the message with the receiver as far as degrees of freedom are concerned. Now again, the same channel, if you have 2 messages that are shared, that is transmitter 2 knows transmitter 1's message, transmitter 1 knows transmitter 2's message, then it's like full cooperation. So you have broadcasts with 2 antennas of the transmitter. You can zero force and get 2 degrees of freedom, which is the maximum anyway. You could also get it if the receivers know the messages, and you can also get it if one transmitter and the other receivers are cognitive. So again, in all these cases, cognitive transmitters are equivalent to cognitive receivers. Now the X channel is where everyone can talk to everyone. Notice in the interference channel, knowing one message didn't help. But in the X channel, even if you know one message, like transmitter 2 knows message W11, which is the message from transmitter 1 to receiver 1. Just knowing one message, in this case, helps. So you would increase the degrees of freedom from 4 by 3 to 3 by 2. And that's not just an inner bound. You can actually show that you cannot do more than 3 by 2. Again, you have to do the same kind of outer bound. And you would find 3 by 2 either way. Now you can also solve these problems for 3-user interference channel or even higher number of users. But for 3-user interference channel, you can show that sharing one message with all other transmitters, all other receivers will not help, just like in the 2-user interference channel. So you will have 3 by 2 degrees of freedom, which is what you would have even without any sharing of messages. However, if you share 2 messages, you will get 2 degrees of freedom. Again, you can show both a converse and an achievability for that. Again, there's so many possibilities, so I'm just listing a few of them. There's the 3 transmitters, and there's a lot of different scenarios for cognition. If you have one cognitive transmitter, that is, one transmitter knows all the messages, but the other 2 transmitters know nothing else, just their own messages. In that case, you do get 2 degrees of freedom, so there is some advantage. Instead of 3 by 2, you get 2. But if you have only one fully cognitive receiver, that is, only one receiver knows all the messages, the other receivers and transmitters don't know nothing and don't know anything, then there is no advantage. The degrees of freedom are equal to 3 by 2. So in the 2-user interference channel, we saw that the cognitive transmitters and receivers were equivalent. But in the 3-user interference channel, actually they're not. Cognitive transmitters are more useful than cognitive receivers. And the reason for that is, if you have a cognitive transmitter that does not have its own message, it can still help other transmitters because it can still send signals to cancel interference.
So I think I know what a cognitive transmitter is. It knows someone else's message.
Right.
A cognitive receiver is a receiver that is like made by Genie or some other means learn some of the other messages
right.
that are not connected for it.
Yes. Yes. But a cognitive receiver, if it doesn't have any message it wants, then it's useless because it cannot help anyone. It cannot transmit anything, so therefore it's not able to really help anyone. All it could have done is cancel its own interference, but if it doesn't have a message intended for it, then it's basically useless. So that's the reason cognitive transmitters end up being more powerful than cognitive receivers. Why do I care about cognitive receivers? This is actually a very common, different form of the problem that you see in network coding. In network coding, we're always talking about cognitive receivers. When you have the standard network coding problem, the receiver knows something and then it receives an XOR. Well, the receiver knows A and it receives an XOR of A and B, and then it's able to recover B from that because it already knew A. That's a cognitive receiver. It knew A and it's able to recover B from that. So cognitive receivers are interesting just from that network coding kind of perspective. So in conclusion, we saw interference alignment is pretty useful. It can make the same MIMO benefits accessible to networks without cooperation or without multiple antenna nodes. It's optimal for degrees of freedom. It may not be optimal for capacity, but degrees of freedom meaning a high SNR capacity. You do need channel variety, which is different from diversity. Variety means the channel needs to change. It has to vary. You need a channel varying in space, time, and frequency. And there's one dimension. It's interesting. This is not fully understood. The variations in one dimension can compensate for variations in a different dimension, but it's not trivial how one dimension can compensate for another. Of course, if you have multiple antennas, that helps because you may avoid the need for these super symbols. You may be able to do with a very short symbol. And for interference networks, we saw that even if nodes have multiple antennas, each user will be able to achieve at least half of the high SNR capacity or the degrees of freedom that he could achieve without any interference. For X networks, where everyone can talk to everyone, we saw that if you have a lot more transmitters than receivers or a lot more receivers than transmitters, then you may be able to achieve the full min mn degrees of freedom that you could with full cooperation of transmitters and receivers. So that's the end of the talk. Any questions?